Alright, in this module we're going to see how we can apply and use bistables, where they might be used in a real problem, but we'll also uncover an issue with bistables that will lead us to our next sequential block, which is called a latch, right, or latches. So to illustrate where we could use a bistable and to also then see the issues with bistables, let's look at the following problem. Let's assume that we need to build a circuit that's going to take in some binary number x, and for now let's make it a 4-bit value. And x is going to change over time. First maybe 2, then 3, then 12, then 8, then 5, some values over time. Okay? And what I want to know, what I want the circuit to do, is to produce an output f, right, to produce an output f that will be true at the end of the sequence, right here, at the end of the sequence, if any number was ever greater than 10, if any number in the sequence was greater than 10. All right? So what this circuit needs to do is detect whether a number is greater than 10, which 12 would qualify, but then remember the fact that it saw a number greater than 10 even after it changes to different values. Right? So there needs to be some amount of memory there. Right? We need to remember that we saw 12 was greater than 10. All right? So we want to say is any number greater than 10. All right. One more thing, though, to help us, we need to know where the one sequence ends and the next one begins. So you may want to do this for several sets of numbers, right? All right. I want to know where one sequence ends, these 5 numbers versus the next set. And so I'm going to have a special signal that, don't worry about how it's generated, but I'll generate it for us. It's called the start of sequence signal. And what this circuit is going to, what this signal is going to do is be true, or 1, when you start a new sequence and then turn off until you get to the next sequence and then turn on again for the first value. So every time you get the first value of a new sequence, that signal will turn on. Okay? Let's see this in action. And here's how we're going to build this thing. We're going to take a comparator. We know we need a comparator because we need to compare our number x with 10. So I just plug in x and 10. 10 is 1010 in binary. All right. And what I'd have out of my greater than output then is a signal x greater than 10, which for each number would compare with 10. In this case of 12, it would go high, but then once 12 goes away, 5 and 7 are not greater than 10, and so it will also go to 0. All right. The start of the sequence signal, again, the way I'm making this up somehow, is that I just give it to you, assume, is that it starts high when you get the first number, so it's 1, and then it stays off until you want to start a new sequence. So this is one sequence here, and then a new sequence starts here. Oops. A new sequence starts there. So it'll turn on again to indicate that. But I want to build a circuit F that at the very end of the sequence, way out here, F will still be true, or 1, saying, yes, I saw a number here at this point in time that was greater than 10. I want to know and to remember when I see a number greater than 10. So what I'm going to do is I'm going to feed them into the set input of a bistable. Because if I ever turn this on, then I'll force F to a 1. But then once I turn it off, it will be remembered. Let's see how this works. Start a sequence then will be my reset input. What that will allow me to do then is to initialize to 0. Because when you start the sequence off, you'll assume that you don't see a number greater than 10 and have it be equal to 0. Okay? So if you realize x greater than 10, that's my set input. Start a sequence is my reset input. And the f output is really the Q out of a bistable. And so really, I'm just doing a bistable waveform. I look at my S and R. I see 0, 1. And that is the reset case for a bistable, right? Activating the R input resets and forces Q to be a 0, which is really F. So F starts off low. Now, once it goes away, I say is 8 greater than 10? False. And so set is false, reset is false, that's the whole case, so I hold. And for this entire time in here, I'm going to be holding because my inputs are 0, 0. At this point in time, it goes high, right? X greater than 10 is high because 12 is greater than 10, which is now the set case for a bistable, right? A 1 on S, a 0 on R. All right, so this goes high. But here's the thing. Once X greater than 10 goes away, right? Once it falls to 0, everything's back to the normal value. What will happen to F? It will stay at 1 because 0, 0 is the hold case. And in fact, then it will be remembered until we reset it, all the way out here. So when the end of the sequence arrives, I can look at F see whether it's 1, and know that some number was greater than 10. Once I do reset it, I'll start all over, and the game begins again. So the bistable can be used to set or to turn something on and then remember that fact. Or, if you want to turn something off and remember that, you could use the R input. So hopefully that makes sense. Let's look at an issue, though, that comes up with these bistables. Let's see it here. Let's say that now the number we have, the sequence we have, doesn't have any number greater than 10. So this is now all false. X is never greater than 10. What would you expect the output to be when you get to the end of the sequence? Well, you'd hope that it's a 0, right? You'd want it to be a 0. But in all likelihood, if you built this circuit, right, and actually plug these values in, when you get to the end of the sequence, almost assuredly, f would be high. F would be a 1. Huh? If x greater than 10, that's the set input. If it never goes high, how could f go to 1? Well, the set input doesn't go to 1 when it's stable for our values. But remember the idea of glitches. Glitches occur when you change your inputs. There's a short window in time from when you change your inputs that the output may go to an invalid or incorrect value. We showed an example in a previous lecture of an AND gate with one input inverted. We said, what if your inputs are 0, 0? Right? Well then, this input is 0, the 0 flips to 1, 0 and 1 to an AND gate is 0. Well fine. What if I change my inputs though to 1, 1? This one immediately changes to 1, but this one has to get through the gate, and there's propagation delay, maybe a nanosecond or something on that order. Right? And so for a while, this output is still at 1. And so the gate sees 1 and 1, which will say, oh, I know that output, that's true. Once this inverter, though, is able to flip the 1 and cause this to a 0, then this will see 0 and 1 and go back to a 0. All right? And so what we have is this momentary lapse where the output is actually true. In a waveform, it would look like this. Right? It might look like that. What's the problem with that? Well, imagine you get one of those glitches when you change your inputs. So you were resetting, F was low, everything was great. You were holding, F was still low, everything is great. Now you get a glitch, right? And the glitch is high, meaning a 1 on S, and so F sets, it goes high. Well, you say, yeah, but the glitch goes away, it goes back to 0. Unfortunately, the bistable then, that's the hold case, and it remembers that glitch, and it will stay at its high value for the rest of the sequence until you reset it. All right? And that's the problem. Just like people have bad memories, humans get bad memories, bistables can have bad memories, right? They can remember something they're not supposed to, all right? And that's in fact the glitches. So what we say is that bistables, right, bistables are susceptible to glitches, and then it will remember that glitch, and that can be very bad in terms of the design you want. Then you won't get the design you expect. Are susceptible to glitches. Okay, and that's, unless you work really hard, most combinational logic is going to be prone to these glitches at the outputs. All right? There's ways to design your combinational logic to kind of avoid glitches, but it takes extra gates and extra work, which we can actually probably solve the problem without having to resort to that. Well, how? How can we solve that problem? All right? The way we're going to solve that problem is the following. Let me walk you through the thought process. When can glitches occur? Glitches can only occur when the inputs change. That's the first thing to realize. Next, glitches can't last forever. At some point, right? So the reason you have glitches is because some inputs arrive early, others arrive late, but eventually they will all arrive. And so after some amount of time, like I've shown here, all the inputs will arrive and your output will be stable and valid at its correct output. You change inputs again, there's a time window where you could get glitches, but then the output will be stable and valid. You change inputs again, there's some time where it will be have glitches, but then it's going to be stable and valid. Right? So glitches don't last forever. So here's what I want to do. What if I could tell my bistable something like this? Hey bistable, we're in a period of time where there could be glitches. So just ignore R and S and hold whatever Q is. Just keep it. Then once glitches go on, once we're past this time, I tell my bistable, okay bistable, R and S are now valid. Go ahead and look at them and update Q appropriately. Set or reset as you need to. Can I do that? Yes, but I'm going to need the help of a new input. What we're going to do is we're going to take our bistable, okay, We're going to take our bistable, and we're going to add a new input called the clock input, or we might also call it the enable or the gate input of our latch. Right? So we're going to modify our bistable and get something new called a latch, and this latch is going to have a new input called a clock, the enable, or a gate. Now, what is a clock? If we call it a clock, we're referring to a signal that is simply an alternating patterns of zeros and ones. All right? Zeros and ones. And what we're trying to use this for is to give us some timing. And we'll see how this comes into play in one second. Okay, so hold on to this. What we're going to do is we're going to take our normal bistable and actually add a next input called our clock or the gate or the enable input. And we're going to run it to two AND gates where then we bring R and S in as inputs. So these are the actual inputs that we used to bring into the bistable directly, but now we'll feed them through a set of AND gates. Well, why? Well, let's look at it here. When the clock or gate or enable is 0, do you see that 0 and anything forces a 0 coming into my bistable? So here's my actual internal bistable. That's just a good old bistable we've seen. And so you could be having a glitch on R or a glitch on S, but will those glitches get through these gates? No, because 0 and anything is 0. Meanwhile, you're getting these glitches on R and S. Q is simply being held. It's being remembered because 0 here at the internal bistable is the hold case. In this way then, I can ignore my inputs when there might be glitches by just turning my clock or gate or enable to 0. Once I know R and S are valid and have no glitches, well, now I want to look at them. I want them to pass through and affect Q. So what do? I just turn my clock input on. By turning it to 1, 1 and anything is anything, the anything passes through, and now R and S get to the bistable and affect it. Okay? Very simple idea. Take a couple AND gates, you're there. All right? But it's very important way to solve this problem. So whenever we do these latches, so latches are devices that have this new clock or gate input. The way all of them work, there will be several different ones that we'll see. The way they all work, though, is when the clock is off, your inputs don't matter, the outputs remain the same. Essentially, you just hold. When the clock turns on, then your inputs are passed to the bistable and the outputs change. Okay? So the outputs can change when the clock is 1. So what's our first latch? Is just our good old SR type idea with this new clock input. So it's a bistable with this extra clock, and now we call it a latch. So I call this an SR latch. And you can see the truth table. All right. So again, when the clock is 0, what's going to happen is this 0 causes zeros to get to the internal bistable, and we're going to hold. When the clock is a 1, then S and R just get through and go affect the bistable, and so what you have is our good old bistable truth table. 0, 0 is the hold case. 1, 0 is the set case. Reset, illegal. All right. So it's simply a bistable that we can choose to ignore the inputs and hold when the clock is 0. Now, if we were to show a waveform plot of this, we should be able to make sense of it. In fact, when we do an SR latch waveform, it's really half of the work that we'd have to do normally, because whenever the clock is low, and you see I've shaded these regions, hopefully you can see that, the outputs cannot change. S and R don't matter. Who cares what S and R is? Ignore them. All right. So when I start the clock off at low, let's say Q initially is 0, and S and R are both 0, 0. Well, that's the hold case. I'm sorry, no, that's not. When you're in 0, you're in the hold mode. Okay. So the clock is off. It doesn't matter what S and R. S could have a glitch. R could have a glitch. Doesn't matter. We're simply going to hold Q. And when the clock turns on, okay, when the clock turns on, I will start to respond to S and R. So for the first point in time, I see 0, 0. That's my good old hold case. So I just keep Q wherever it was. But then halfway through, I set. S turns to 1, and so Q goes high. Right? Q goes high. When the clock turns off, whatever the last value I see before the clock turns off, that's what I remember for the rest of time until the clock turns on again. All right, so I remember that value while the clock is low. And so what you have going on is, notice even this, you have some illegal case going on. All right. So in that scenario, you can't, it's not going to affect anything because you are in the hold case, right, because of the clock. These guys aren't even getting to the bistable, and you keep it up. All right. Now, you fall back into the reset case, but again, it doesn't take effect until the clock turns on. Now that you have the reset, you fall down to 0. All right. So it's only when clock goes to 0, only when the clock is 1 that you will update your outputs. Okay? When the clock is low, you hold steady. A little glitch, though, will still cause due to set as long as it happens in the clock high time. So if you're going to use a latch and you want to avoid glitches, make sure they happen when the clock is low. We see another example over here, and you can trace through this. Here I have a glitch, but it's when the clock is low, so my output Q is not going to necessarily respond to that. And again, we can ignore whenever the clock is 0. Everything there is ignored. Everything shaded is ignored. So my solution to our original problem of our sequence is that I'm going to change my inputs when the clock goes low. Right when the clock goes low, I'm going to cause a change in my inputs. That's when then glitches could occur, but because the clock is low, they get filtered. Right? The clocks get filtered, which means my output won't get set. It'll just, essentially my output stays low. When the clock turns on, then I'll respond to things, but by that time the glitch has gone away. So by using this clock and by essentially changing your inputs or having glitches occur when the clock is low, you can avoid having those bistables catch the glitches and remember them. What that means then is the following. You would then want to set your clock period time, all right, or your clock low time for the delay of the circuit, right? If it takes, 5 nanoseconds for all the inputs to arrive and the outputs to stabilize, you'd want this to be at least 5 nanoseconds because that's the time window in which you can get glitches. So really you'd set your clock period based on your design and how long you need to avoid the output glitches.